Welcome to Module 11, Boilers, Steam, and Heating Water. In this module, we move from cooling plants into the heating side of the building. Heating systems can look simple on a BAS graphic, but in the field they involve energy input, combustion boundaries, pumps, valves, return temperature, minimum flow, staging, steam behavior, and freeze protection. The goal is not to turn the BAS into a burner safety controller or a boiler technician. The goal is to help you understand what the BAS can responsibly observe and control, what must remain inside certified equipment controls, and how to make better heating plant decisions using evidence. By the end of this module, you should be able to explain boiler output in practical terms, respect combustion safety boundaries, evaluate condensing boiler performance, review heating, water reset, recognize short cycling, and understand the basics of steam and freeze protection. The field mindset is important. A BAS can coordinate heating systems, trend temperatures, enable stages, reset set points, and alarm abnormal conditions. But it does not replace certified burner controls, flame safeguards, pressure relief devices, code-required safeties, or the authority of qualified boiler personnel. This overview shows the big picture. A heating plant can include hot water boilers, steam boilers, pumps, headers, control valves, coils, air separators, expansion tanks, condensate systems, and safety devices. For the BAS professional, the main task is to understand the path from energy source to useful heat at the load. If a space is cold, the answer may not be a simple set point adjustment. The issue could be boiler enable, low firing rate, wrong reset schedule, insufficient flow, air in the loop, failed valve, fouled coil, steam trap failure, or a freeze protection response. Always trace the complete heating path. A boiler transfers energy from fuel or electricity into water or steam. The BAS usually does not control the combustion process directly. Instead, it coordinates heating demand, enables equipment where appropriate, manages reset strategies, monitors temperatures and status, and alerts the operator when the system is outside expected conditions. A professional BAS review starts with the boundary. What is the boiler controller responsible for? What is the BAS responsible for? What safeties are independent? What conditions must exist before enable? That boundary protects people, equipment, and professional accountability. This slide is critical. Combustion equipment has safety controls that are designed, certified, and maintained separately from ordinary AS logic. Flame safeguard controls, gas proving, high limits, pressure relief, low water cutoff, and similar devices exist to protect life and equipment. The BAS may request enable, coordinate staging, reset water temperature, display status, and generate alarms, but it must not defeat or simulate safety functions. If a safety trips, the professional response is to investigate the cause and involve qualified personnel. Never use BAS programming to hide or bypass a combustion safety problem. Input is the energy supplied to the boiler. Output is the useful heat transferred into water or steam. Efficiency is the relationship between the two, but the boundary matters. A boiler-only number is not the same as a full plant number. In BAS work, avoid comparing numbers with different boundaries. A condensing boiler may have excellent rated efficiency, but if the return water is too hot, if staging is poor, if the plant short cycles, or if pumping energy is excessive, the heating system may perform far below expectation. Condensing boilers recover additional heat by cooling combustion products enough for water vapor to condense. That benefit depends heavily on return water temperature. If the return water is too hot, the boiler may run like a non-condensing boiler, even if the equipment is labeled high efficiency. The BAS professional should trend supply temperature, return temperature, firing rate, outdoor air, runtime, starts, lockouts, pump status, and valve behavior. If return temperature is high, do not only adjust software. Look for physical causes such as three-way bypasses, oversized coils, poor valve authority, excessive flow, or reset schedules that are too aggressive. Heating water reset lowers supply water temperature when the building does not need full design heat. This can reduce distribution losses, improve condensing boiler performance, and reduce overheating. But reset must be bounded and tested. If the reset temperature is too low, critical zones may not recover, coils may underperform, and operators may override the sequence. A strong BAS review asks, which zones prove the reset is acceptable, what is the recovery strategy, what are the minimum and maximum limits, and how does the reset affect boiler efficiency? Multiple boilers should be staged using more than one clue. A sequence that enables too many boilers at light load may create short cycling. A sequence that waits too long may fail to maintain supply temperature. Good staging uses load evidence, firing rate, supply temperature error, runtime, minimum on and off times, lead lag rotation, failure behavior, and trend review. The professional question is not simply, did the boiler turn on? It is, did the plant enable the right amount of capacity for the actual load? The BAS sequence must reflect the actual boiler and piping arrangement. Some boilers require minimum flow. Some require return temperature protection. Condensing boilers may benefit from low return water temperatures, while other boilers may be damaged by sustained low return temperatures. This is why copying a sequence from another site is risky. The BAS professional must review the manufacturer requirements, piping, pump arrangement, bypass or decoupling strategy, sensors, and safeties before changing flow or temperature logic. Steam carries latent energy. When steam condenses, it releases significant heat at nearly constant temperature. That makes steam useful, but also demanding. Condensate must be removed, steam traps must work, pressure must be controlled, water hammer must be treated seriously. The BAS can help by trending pressure, temperature, valve position, pump status, alarms, and trap monitoring where available. But steam systems require proper mechanical design, maintenance, and qualified response. If the system shows water hammer, flooding, unstable pressure, or freeze risk, treat it as a priority. Water hammer is not a nuisance. It can damage equipment and piping. In steam systems, condensate can collect and then be driven at high velocity. In hydronic and air handling systems, freeze risk can destroy coils and flood mechanical rooms. The BAS should not hide these conditions. It should provide clear alarms, reliable sensor placement, appropriate interlocks, trend evidence, and escalation according to site procedure. Operators should know which alarms are urgent and what action is required before damage occurs. Calculations should support field judgment. If a boiler receives 1 million BTU per hour of fuel input and operates at 90% efficiency, the useful heat output is about 900,000 BTU per hour. If the water side shows 90 gallons per minute and a 20-degree temperature drop, the familiar HVAC approximation also gives about 900,000 BTU per hour. When two independent checks agree, confidence improves. When they do not, investigate units, flow measurement, sensor calibration, operating state, and system boundary before making changes. This case study comes directly from the field pattern many BAS professionals see. A modular boiler plant short cycles because staging is too reactive for the load. Multiple boilers start in mild weather, then shut down quickly because the plant overshoots. The correction is not simply to raise the heating water temperature or disable alarms. The correction is to improve the staging strategy. Use persistence, minimum runtime, firing rate evidence, lead lag logic, and proper plant feedback. Then verify the fix by trending starts, runtime, supply temperature stability, return temperature, and comfort. These mistakes create risk. Never treat ordinary BAS logic as a replacement for burner safety controls. Never copy a sequence without verifying the boiler type and manufacturer requirements. Do not assume a condensing boiler is actually condensing unless the return temperature supports it. Also, watch for reset curves that underheat critical zones, staging logic that short cycles equipment, minimum flow problems, and freeze alarms that operators have learned to ignore. Professional heating plant work requires evidence, documentation, and respect for limits. The best answer is C. Short cycling during mild weather usually means the staging strategy deserves review. The plant may be enabling too much capacity for the load, responding too quickly to temperature error, or operating with return water conditions that limit condensing performance. Forcing more boilers on can increase cycling and energy use. Disabling alarms hides the symptom. Lowering room set points does not address the plant behavior. The professional response is to evaluate load, staging, reset, firing rate, minimum runtime, return temperature, flow, and the actual system arrangement. For the practical assignment, students should review a heating plant before changing the sequence. They should identify the safety boundary, confirm what the BAS is authorized to control, collect trends, evaluate reset and staging, and recommend one safe improvement with a verification test. The key takeaway is that heating systems are not just winter comfort systems. They can affect safety, freeze protection, equipment life, energy cost, and critical operations. In the next module, we move into electrical fundamentals for BAS, where measurement, control power, signals, and safe work boundaries become the focus.